All right, so thank you everyone for coming. My name is Patrick Hellman, and I'm going to be talking briefly about buffalo grass distributions in southern Arizona, how a model was built for them and used to predict buffalo grass distributions under a number of different climate change scenarios. So first, going to go over a little bit of background and then cover some information about how the model was built, how it was used to forecast future distributions, and then just some general takeaways. All right, so buffalo grass is a perennial bunch grass that is native to much of Africa and the Middle East. It's a dry season C4 grass that is really well fire adapted. It has a very deep taproot and can survive even high temperature fires. It's also has a lot of production even in sort of the driest years. So it has been seeded in many places around the world for use as a cattle feed in drought prone areas like Mexico, the southern US, Australia. And you can see here all the different places that it's been introduced. And in many of these places it's been introduced, it is now considered an invasive species. Most of the introductions were done in the late 1800s, early 1900s. And here in southern Arizona, it is spreading very rapidly. A recent study showed that it's doubling in population distribution every 2.5 to 7 years since 1988, and it is becoming quite an issue in some areas. That's some of the issues that it can cause. So one of the problems is it will move into the interspaces between typical Sonoran vegetation and allow fire to carry much faster and much hotter through the Sonoran environment. And that has led to some permanent soil damage with a loss of soil ability to fix nitrogen and a big reduction in biodiversity. Actually, there were some studies in Australia that showed that presence of buffalo grass is now the largest indicator of biodiversity for a specific area, even greater than rainfall, how big of effect it can have on biodiversity. And when it moves into an area, it has the potential to really convert the area into a buffalo grass dominated grassland and really just get rid of whatever was there before it. So what we're attempting to do is to build a model that will predict current population distributions of buffalo grass here in the Santa Catalina Mountains in southern Arizona, what some of the leading environmental factors are that play into its distribution, and then how that distribution might change between now and the year 2100. So just quickly looking into how the model was constructed. The data used for this model came from the United States Forest Service National Invasive Plant Inventory, and from the climate data came from worldclim.org. The invasive species data came in the form of polygons that were then changed to points using the center point of each polygon. And then the climate data came in the shape of rasters, 19 different bioclimatic factors for a number of different time periods, as well as for 3 different scenarios, light, medium, and heavy scenarios for climate change. And these were used as the data in a presence-only maximum entropy model. This model was chosen because we had presence-only data, and we don't really know all the other points. We know that where we have points, buffalo grass is present. Everywhere else, it might be present, it might be not, we're not sure. So this was sort of the ideal model to use in that situation. And we have our presence points, which are where buffalo grass is present. This comes from that invasive plant data that we got from the Forest Service. And then there's an auto-generated grid of background points for the whole study area where buffalo grass may or may not be present. And then the environmental factors at these presence points versus the background points are compared to try and generate a function to see where buffalo grass is most likely to be. We did spatially thin the data a little bit, as some of the buffalo grass presence points were really close to each other, and we didn't want to sort of bias the data by having a whole bunch of points right next to each other. So we did thin it out a little bit. So this is sort of what the general model looked like when it was first created. You can see the probability of presence was broken into 4 different categories, ranging from 0 to 25%, 25 to 50, 50 to 75, 75 to 100. And what we did is we took that And anything where the probability of presence was greater than 50%, we considered to be probable bufflegrass habitat. And anywhere where the probability of presence was considered to be less than 50%, we consider was not probable bufflegrass habitat. So then we reclassified our model and built a sort of a final shape that showed what is probable bufflegrass habitat under current environmental conditions. We validated this model by taking essentially a third of the data set and at random, and then comparing it to the model that was created. And we did this 3 separate times. And the model was able to correctly identify bufflegrass presence about 91% of the time, and only misidentified background areas as presence about 2% of the time. So that was really better than what we had, better than the thresholds that were set out when we first started to build the model. The leading environmental factors in this model, or the environmental factors that had the greatest effect on the probability of bufflegrass, was the variation in precipitation between seasons, the minimum temperature in the coldest month, and the mean annual temperature. This was also a really good thing to see, as in a lot of the literature and in sort of just the background knowledge of bufflegrass, it's not a freeze-tolerant plant. So seeing that minimum temperature in the coldest month was one of the leading factors that was limiting its distribution showed that this model is doing a really good job of mirroring what we see in the real world. And you can see right around 0 degrees for minimum temperature, probability essentially goes to almost 0, which is what we see and what we would expect. So that was a good thing to see. All right, so how was this model used to forecast future distributions? So we took this model, and what we did was we had environmental rasters for what likely environmental conditions will be under a light, medium, and heavy or severe climate change scenario at 4 different time windows. And we matched these rasters to our original rasters that we built the model with, and then used the future climate conditions as prediction rasters to model where bufflegrass might end up being under those future conditions. And you can see here the results of that. SSP1 is the lightest climate change scenario, SSP2 is the moderate one, and SSP3 is the most severe climate change scenario that we used for this. And you can see typically on these maps, the bufflegrass is moving towards the northern end of the mountain range and then up in elevation. And in our light and moderate climate change scenarios, we saw an overall habitat increase right around 280%. Those were almost the same as far as overall increase. While under our really severe climate change scenario, we saw a 500% increase in bufflegrass distribution, or in potential habitat anyways. And then just looking at the actual number of kilometers of potential bufflegrass habitat under each of these scenarios, you can see again that the light and moderate one end up sort of in the same area, but the lighter climate change scenario, it declines much earlier as far as how much potential habitat there is, while in the moderate scenario, it continues to increase all the way up to 2080 before it finally starts to decline. While under the most severe conditions, climate change scenarios, it just sort of keeps continuing in a linear fashion, and we end up with much higher potential bufflegrass habitat. So just some general takeaways. The maximum entry model was definitely an effective model for modeling bufflegrass distribution. We sort of knew that going into this, as it had been used previously in a number of other studies, but the model really did, in all of the metrics that were used, it greatly exceeded all of them. We had a goal of an area under curve value of 0.8, and we ended up with 0.99. And for our original validation, we were hoping for a 90% of predictive ability for actually getting where the presence points are, and it was over that as well. So it worked really well for that, and it also was really effective at mirroring what we see in nature and what we know about the plant's biology So that was it really was a very effective model for that. We did see that, you know, buffalo grass habitat is expected to increase regardless of climate change conditions. It's going to increase. How much, however, you know, is somewhat dependent on how severe climate change gets. And then there's also the potential of feedback loops, as, you know, buffalo grass isn't as effective at carbon sequestration as a number of the other species that are already present, and it increases fire frequency. So there's sort of this feedback loop where the more buffalo grass you get, the further it's going to spread, the more of it you're going to get, the more damage it's going to do. And so definitely something to think of as climate change continues, if it becomes more and more severe, we should expect to see this become a bigger factor and increase even further. The changes in habitat distribution were mostly spread throughout the mountain foothills. Typically, it was moving up in elevation, which sort of fits with what we looked at as far as environmental factors. As those minimum temperatures in the coldest month go up, it's able to increase in elevation and survive in some of these areas that it wasn't able to previously. So knowing that the opportunities for buffalo grass to spread will be numerous, be really important in the future, and to focus on preventing new introductions and containing the current ones. So we know it has this, you know, great ability to spread. So the goal would be then, if we know it's going to spread, and we know that a lot of the spread will typically be, you know, in the mountains, moving up in elevation, moving to the northern side of the mountain ranges, that's really where we should focus our mitigation efforts and prevent it from being able to establish in those areas. And we can focus on preventing buffalo grass from spreading into those areas that will become more susceptible as the climate starts to warm. All right, are there any questions?